All right, yeah, so welcome back and welcome also to our online audience. Now we have the final lecture, which brings together all the different bits and pieces we had established before, from support vector machine, the regularization parameters that we still have to find. It's a process called validation, and I would like also to put it in context of support vector machines, together with all of you, then doing a kind of a group assignment and filling an interesting thing called grid search. It's not obvious to you, we will see how that materializes throughout this last lecture. And take away the message that here is the most parallelization benefits. Why? We will explain. Now you have already experienced the speed up by using basically the parallel version compared to the normal libSVM. And this would be the same if you use MATLAB. We did most of our studies comparing MATLAB with our parallel implementation. And in most of the cases we had a significant speed up, sometimes even under a minute. And of course in that kind of sphere, you talk more about real time or more of real interactive behavior. Right? While in MATLAB sometimes it took 15 minutes, so we can get out, take a coffee, come back. When you have a 1 minute job, right? And if you increase the number of cores, usually you should always come close to this 1 minute or 1.5, which is really the I/O limit then, where we cannot improve very much more. Basically, this is already very nice because then you don't need to leave the room and wait for the results, you can just do it. However, this was internally in the algorithm, so we kind of parallelized the algorithm, make it much more faster. Now the question remains is what we can do as a whole when we're searching for parameters. And this is a process called validation we will go through. And we do this also with libSVM. Before we do this, let us just, as usual, review a little bit what was the theory about support vector machines. Just quickly, because it was basically just half an hour ago. We said we basically can, in generally, do nonlinear transformations, which means we basically do something like we transform the data set to some interesting mapping function called phi. Could be anything you define on your data. One example that we had, we put it from a 2-dimensional space to a 3-dimensional space, right? And then we do our machinery in this interesting so-called feature space and do basically a line there, right? Or here is a hyperplane example because in the 3D example. So we still do our usual optimization. And the interesting property that support vectors have is it's an in-sample property what the support vectors are. So we are able to kind of map that back to the input space to the initial one and see with this we have a highly nonlinear decision boundary created inside the higher level feature space. And this works pretty well because support vectors are an in-sample property of the optimization process here. The optimization process itself was the Lagrangians that we established before. So in many cases this alpha will be just 0, right? And those zeros doesn't contribute to our support vectors. So you do all of this just for the support vectors. Hence, less reduction in computing. And the beautiful thing is we've seen that not only basically the Lagrange optimizer is a dot product, also in the end the decision rule is one. And we just stick in there several trusted kernel that basically should transform our data into some sort of feature space. But as we have seen in the kind of definitions and in the example in the last time, actually computing then phi necessarily this mapping sample by sample is not needed to do it directly. You wait until the kernel gets initialized, and we had the kernel from the polynomial, the RBF kernel, that then in many times does not really require to compute these mappings. Hence we visit kind of a phi space that we will never know. This is somewhere in the feature space. We do basically the kind of optimization there, and we don't pay the price for all the samples, right? In the sense, we have there a very nice property in terms of computing also with this kernel trick. And of course, apart from this nonlinear transformation that you inherently do of getting it all a hyperplane, we also save computational time by sticking in this kernel. However, creating a kernel yourself is not something that you do on the weekend, come back and then you have a very good kernel. This is something where you require Mercer's conditions to hold, and this is a big topic, so to speak. There are whole workshops around creating your own kernels. So hence, when you have an application domain problem, use the trusted kernels that are available would be my recommendation first. Use RBF, think about the parameter gamma and the parameter for the polynomial kernel. And this alluding actually to those things we will do now. So lecture 4 left a little bit with a sad note of not knowing which cost parameter I should take. Right? You remember we take 1, that was the default, but why not 10 or 100 or 1000? Right? And the other part of the game is we had now, interestingly enough, the RBF kernel, which has this interesting fellow gamma in lecture 5. Now we said, it's a nice kernel, but how do I pick 4, 8, 16 or 32 for it? How should we know and how we should get to it? And this is a kind of concept called grid search, where you basically have now to find the best parameters in order to perform your model selection. It's not my idea now to write on the board all the time. I have lots of slides, but still, this is a kind of group assignment we will do together, while basically I have basically a little bit at least from the theory of validation explained. We also compute in the background then all the cross-validation runs basically for this model selection phase. Right, so let's go and think about what is this kind of validation. So this is an interesting aspect because in many ways you should have always a validation set also. And here and there I discussed with this with you already in the break, right? So you have a training set, a test set, and if you have very much data to spare, keep several validation sets. And the reason is here for exactly this lecture, to perform model selection and validation. We talk about this. However, if you don't swim in data, you don't have so much data, what usually happens in engineering and science, you have a trouble of kind of cutting them into training tests. You will have just not enough samples. We talk about this. Hence, there's a trick afterwards called n-fold cross-validation technique. And who is using cross-validation in practical settings? Now that's what basically is really de facto standard today of really using and performing model selection on your data. However, there's a kind of small part with it when we talk about data contamination, and I will make a specific point of it. Of course, we want to then apply validation to our Indian Pines or Rome data set. This is, of course, interestingly, and if you want, you can also try that a little bit with your libSVM. But this group assignment here that we have is much more interestingly, so contribute basically then in the parallel version with our grid search. That's not obvious to you. We'll see how that materializes now after a little bit introduction, what validation really means. However, I would like to conclude our tutorial with this special meaning, especially in the domain now today with big data. You have heard that in the media, often considered a hype, but we see already that using a parallelization and using clusters and so on brings the speed up, so really accelerates the big data analysis, right? And then on the other end of the scale, the data management, if you think about we're facing now terabytes of storage, in the future petabytes of storage, where we also in machine learning are dependent on. We need data, right? Now everything was for you happily prepared on the parallel file system. Think about that this also costs, and the storage will increase the more we get new data in the future. So that's interesting, and parallelization scales with these demands, right? So this is where we see more and more we will work in the future with large data sets. You can always here and there downsample, but then you also lose much of the relationships in the data. Depends, of course, as your application domain question requires it. And then a little bit as a summary and acknowledgements, we bring the team here on board, so be prepared that I have everyone here from the Ghent team here on board. We basically talk a little bit at the end about some complex applications that you will find in practice when you go out in the field, industry, jobs, and so on. What would be real challenges like in medicine and so on, and talk about this data contamination throughout, basically, which is again the point in validation. So we come back to our cross-validation run to make a specific impact point of saying there's where the most benefit is in parallel computing or using parallel computing in machine learning. Right, so validation. We have heard now of basic building blocks, and we basically don't really have to change something on this kind of general approach. Right, all what we think about now is a little bit about this training examples. So as we know, we have kind of this training examples, there are labels to it, that's not new to you, But what we've done in the past, we kind of get them, we assumed it comes from the probability distribution as any other sample, and we cut it. So one question was alluding to, we cut it at 10% training, for instance, and using 90% test. That's not what you need to do, right? It is an application domain question depending on how much data you really have. But if you have, let's say, enough data, that would be a good start. If you see that the training doesn't work, you would increase to 2080 maybe, and then maybe to 3070. Because if you remember on the Wapnick-Chervonenkis inequality, this was this interesting fellow minus to the power minus n, right? So this means the more samples you have, the better is the probability that the out-of-sample performance follows the in-sample performance. So if you have too little samples, you know this harms. But this is alluding to another problem we have now when we want to also create a validation set. Right? We need a training set, test set, validation set. And we have actually all of them trying to get our good training examples away. Right? That we need to train well. On the other hand, we need good validation to estimate our out-of-sample performance. And then we need a good test set to really check if our model works well. So all of them we bring now in one perspective in this lecture. But since, you know, we don't really, the fundamentals here, that's what the key message to take away from this one is, we don't really change the overall philosophy, how basically machine learning is done. It's just basically the professional edition of picking parameters right. So just for you, remembering model decisions, right? With respect to model decisions, this is now the key task of validation. Model selection, model decision. Right? And this is an interesting thing. We have here the kind of target function that we always know. We had this training and test set. And this is something now what we have to review a little bit. That's why it's red. Right? So let's see what can we do with the training set, with the test set, in order to think about a validation set. So when you think about the model selection process, again, basically what you do in testing was very simple. We didn't go through all this hypothesis, right? Just as a kind of going through what we mean with model selection. We have not, again, basically to the point, in a way, we have infinity of models. We are now machine learning, you know, we know already SVMs, we know perceptrons. Next week you will learn artificial neural networks and deep learning, or some of you. So we have already in our skill set quite some models. And all of them is something what I could use for training. Hence this M factor that we reduce then to this in-sample quantity. But still, the idea is that, you know, this hypothesis search will not stop. You still go through all your models, right? In a sense, it's hopefully not infinite of M1s. You pick the model you choose, and then we know by just concentrating on the samples through the growth function we had, we can still learn. So it's not infinity when we pick the model. However, testing is very simple. Once we have defined the hypothesis, you can just evaluate, right? So this is not in the moment the key concern. So we have much more a problem of saying when we cut away lots of training samples, that's what I was alluding to with the minus n here, then we have also a problem here. Still, the question is which hypothesis to pick, right, from all of these models. And why we pick this validation set is related again to the problem of overfitting. What you have already learned in lecture 5 and a little bit in 4 was regularization. So we said, like, when overfitting occurs, like here, you know, or generalization, error out of sample goes up. That's where overfitting starts. So basically, don't really take every kind of sample by heart. We penalize the model. You already learned that, right? In a way, that's your cost parameter that you have just explored in the SVM. You know, your margin, even if there's some outliers on the other side, even if we see, you know, they would, you know, contribute to a very, very small margin, we ignore them and get the margin better in order to have a better generalization again. Hence, regularization, right? We don't take any sample and create a wiggly curve. We still, you know, create a perfect margin by allowing some errors. Hence, this is the same idea with regularization, but we left on a sad note and said, well, that is just one part of the game. So what is validation? That was the second part. When you think about learning, you really have these two solutions. As we remember, we talked about what's the reasons for it. This is largely noise, and basically the hypothesis that you try, basically that you have in your skill set tries to fit all of this noise. So we have to work on it. And this is something where regularization helps, but also validation. So validation is fundamentally different than regularization, right? In the sense that it's a completely different process. It is much more like training in a specific way to find out an estimate out of sample. So you don't create a model. Instead, you just give an estimate out of sample. And this will be a key property. Yes, there are kind of different terminologies in different parts. So validation is basically then what you do in terms of what we see here down there. We kind of split the data in a training and validation set again. And you have lots of variance and variability in this when you do random splits. So it's probably also not a good idea if you then train again and validate again on all of these different samples. So there must be a systematic way of doing it. Otherwise, you can do random sampling. Some actually have talked with me in the break against this. You have to take care that you have picked the samples right for this. And this is something which we, of course, think about more in a systematic way. So this would be the addition. We perform validation in a systematic way. And the system will come. Bear with me. The test still would be important for us. We throw the test set in the corner, and this will be something we still report then to our customer, right? We don't skip now testing and say we do an estimate of the performance. We just use the validation set for model selection, right? We select a model in order to estimate which will probably come out. The training error will be also still the same. We still train our models, right? It's not that we stop now training. So once we have the selected model, we train on the selected model and then test on the selected model. So in a way, it's an additional process we talk here, in a systematic one. So when you look, there's a little bit what we want to achieve with the overfitting and the better generalization. You can see it perhaps a little bit like this, right? That you have, if you remember a little bit, the in-sample performance plus here the overfit penalty that we try to really get with the regularization kind of a grip on. So this penalty that we add, it's just something of saying we don't take our in-sample errors so by heart. We add a penalty because we know there will be lots of noisy stuff that we basically fit here. So let's add an overfit penalty. That's what we have done before. So what validation will do will just give us a glimpse on what's happening here, right? And this is an interesting stuff for us. And we don't touch the test set for it, right? We just take the typical, let's say, training set. We will see how that materializes when we use cross-validation and so forth, in order to get a glimpse of that. So we also should rename that a little bit. It's not anymore the actual E-out, right? The actual E-out is something we will never know, because this will be unseen data set that come in the future, right? And I hope I'm prepared for that. But what we will do is we have then estimator, right? An estimated out of sample. Now the problem is, I already alluding to in the overview, we have just a couple of samples, right? And we have to cut this now for training set and test set. That was already a complexity where you think about, okay, how I do this. Now when you do a validation set, you have to cut again, right? Those that are involved in validation. And this brings a problem in learning at the same time, because when you remove things from training, you train not so well anymore, right? It depends now on the amount of training sets that is available, and the same for the test set. When you remove it very much from the test set, this validation set, then your reported accuracy will be probably not really correct, because you don't have lots of samples in the test set. So we have here trouble now of competing around basically the samples that are clean. Hence clean means something like when we used the data set for something, it's often data contaminated. It's normally a whole university lecture, but because of the time here I could not really talk about it. It reflects a little bit like when you use a training set to perform a model selection, there is a bias inside already. You learned already from this step, and with this it will not generalize very well when you use it for model selection, hence the validation step. But we will come to that step by step. Now here's a little bit the estimate. Now we can do this basically repeated number of times. The estimate is in a way nothing else than testing something, right? So we have the labels here, f of x, like is y. We could use like squared error. So the error measure for using this is not a problem in a sense. We know how to estimate the out of sample performance, right? Now the interesting new thing we add a little bit here is a probability theory of saying now that, you know, we use a little bit an estimate that is reliable for that by putting the expected value in front of it. And the expected value just reflects a little bit again to the probability. You just have to do it often amount of times. Right? And this is a kind of repeat the experiment that we have here, the error, and basically, you know, calculate this just a number of times. This is kind of the expected value quintessence, if you want, in the end. And this is a little bit new to get the estimator towards out-of-sample performance. It's a little bit derived from statistics, this idea of this, because basically what you have is this high variances, and they would like to get to a more reliable estimate, and I have some examples that really show that. And if you now have the idea of putting these kind of, you know, cache here inside the training sample, for example, you know, those will be involved in training and test, and these for validation, then you assume you have kind of k points for validation, and you put them in your validation kind of error. So the expectation, basically what you get, you sum them up often enough of times, and then you basically, if you do this experiment, and if k is large enough, right, if you don't just do 1, 2 validation points or samples, it doesn't help you. That's also one part of this. You need lots of samples to have a reliable estimate. Hence, we're talking more and more about this trouble factor k, right? Where actually can we cut here? And the reliable estimate will only be given if k is large. If you know a little bit about statistics, what the expected value is saying, you have to repeat the experiment quite some often times to get a reliable estimate then about the expected value. Hence, this is only going to work if we cut lots of samples away from training. However, we just said with Höfding, and actually then Dudnik-Chervonenkis inequality, we need lots of n samples to train to have a good out-of-sample performance. So we more and more come to the problem now, the conflicting factor k. And there's a cure about that I want to show. However, at that point in time, usually my students are questioning how it works now all in all. Right? So now they are a little bit confused, and I think here and there I see also some confusions in the phases. Now we have training, testing, validation, when is what, and how I do basically all the process. So that's why I have here basically the overall view, how you basically now would perform basically the task before we really talk about, you know, cross-validation. Just all the formal way would be now putting everything in the pot, what we learned. So when you now really face a problem, and this is a formal way, right? So when I say now, let's say a couple of things informally in front, would be, of course, you experiment a bit with all the different models, right? You use data sets, you analyze them with trees, you analyze them with neural networks, with SVM, but don't get stuck maybe in the model for more than a week. You switch and think maybe decision trees or better random forests, ensemble methods. That's actually better than the neural network I had last week. And you experiment a bit. Once this experimentation phase is done and you have a very good idea that one of these models is probably very good, you start doing this more formally. So this reflects now this model selection process. And this is actually independent of saying the following. So we have this different hypotheses that are all derived here from our hypothesis set. It could be artificial neural network, support vector machine, or deep learning algorithm. However, it's the same for saying we have an SVM with a polynomial kernel, an SVM with a linear kernel, or an SVM with an RBF kernel. All of them have different parameters. All of them are different hypotheses for the problem. And it doesn't matter on which level you are. Are you between different models? Or basically are you within a model, let's say support vector machine, and you have to select, right? So this will be always this level. Now, if you remember what we established in the theory, want to typically train, pick G, and you do this basically on the training set, right? But now having all of these models trained is not a good thing to do, because once we train there and then pick a model from that, this data set would be contaminated, right? This is a problem that we learn already by picking some of the models out of the data, and there's a bias then in this data set that it will be not any more reliable to do further work on. Hence, using it for training for the model selection process will be not very good. Hence, as we said before, we do something like an estimate out of sample. We keep the training set, cut away now validation, right? Validation sets. So basically this is then giving you all the different ideas, using it with a validation set. This is the first step, right? Then you do this and you can report what one would be the best on the validation set. You don't create a model, you just have an estimate of the accuracy, right? And this is an interesting part of it. And then we just pick the best. In the moment where we pick the best, we have actually contaminated this data set, right? So data, well, should basically be not anymore used. And if you have enough data, it is good to have it somewhere, you know, in the site and then throw it away, not touching it anymore. So this is the validation set idea. Now when you pick the best one here, you have done your decision. What usually is, you put all of them back in the pot, right? Because then when then you train again on this best fellow as everything again. Left alone this one because it's contaminated, biased. And this is of course still the problem of K that we will now have a fix for with cross-validation. But this is an interesting thing that you then do in terms of the overall process of saying then once you train then everything again, you have your best model picked, then this is what you report basically as your final hypothesis, which is the one that you got out of validation, right? But out of validation just get an estimate. So you throw away the validation set and train again with the best parameter, and interestingly enough the accuracy will change, right? When you do it in a practical setting, you usually have more an assignment for students around that, which takes much more time because these cross-validation runs are long. Then you will see basically that the accuracy quite improves because the bias is gone. When you put this back in the pot, you usually have a problem, right, in terms of accuracy of using all together then for training. You can try that out and we really see that the accuracy is not anymore the same than having a clean set. Of course, this depends a bit how much training sets you have in general. Right? As I said, the trouble of K still remains where I cut the data. And this is best explained a little bit here. Right? That is the point I will specifically make here. Choosing now, basically the trouble is in K, where I do the cut. If I do more for K in training and I say I leave much more for training, I'm very well suited for the out-of-sample performance. I can be very sure when I train a lot, I have lots of training sample, my output, basically that I give, then using the test set, my output would be reliable out of sample. However, the problem I have then is I have nothing for validation. So I will automatically contaminate then with, again, my model, so this would be automatically reduce the accuracy. And then on the other side of the scale, when I say, okay, when I include many of them in validation, we know the estimate out of sample would be very good. We keep the clean data set for training then, would be also better the accuracy, but we have less samples to train. So it's a bias and versa, right? So we get a better, cleaner data set, not a bias, because the validation set is thrown away for model selection, but we have the trouble of not having so much training examples again. So this is a trouble around parameter K in the middle, right? We need both, right? And this is of course a key problem now. How you can do both, basically not really possible. Right? Either way. However, this motivates our cross-validation trick. And basically, if you know a little bit about iterative methods in numerical approximation and all of this, it's a little bit derived in a way, the thinking like this. Instead of doing all at the same time, think about now in time step, do another dimension to the problem, and use basically one after another. There's a trick, repeat the number of trainings on different subsets. Basically multiple times, leave one out, leave more out. I will talk to you what that means exactly. But this is now the big gain that is actually used mostly in practice. With this, you can basically now use a whole training samples that you have for validation. But you do it in a systematic way called cross-validation that keeps the bias extremely small. The data set is still contaminated, right? It has a bias. But the bias is relatively small because we do it in a systematic way, capturing the variance and all of this. So how we do it? Actually, it's not really so kind of complicated. If you think now, the only thing we add to all of that, what we discussed, we don't do it once, we do it multiple times. And already this rings a bell in those of you who know a little bit about parallelization. If you do things multiple times, maybe we can do it parallel, right? So what we do is here, for instance, in leave one out, which would be perhaps the best solution, the best model you can have, right? You would say you split your data set, actually not really in just two completely different sets. You do an iterative approach. You go through the data set now and take, always n-1 data points. And you use them all for training, and you validate on one you took basically for validation. Admittedly, if you have, let's say, 1 million of data points, this will take very, very long, right? So this is not maybe something in practical situations useful, but the idea shows you that you basically get with the bias, you swallow this bias in a sense by iterating over time through many, many time steps. So, and when you're done this, you do the same on the next subset, which is illustrated basically here, right? Then you put the other one you validated on it back into the pot, and the one you had before is then used, for instance, for training again. So you always leave one out, basically, and then with this, you put the estimate over all of them, and then kind of run to this interesting thing that you can report something over all of this kind of aspects that you do, one by one. Leave one out, train on them, put the one back in the pot. It's called resampling, right? And you do this, of course, now n different times in the data set. And this is now interestingly, because when you think about computing need, here you can now really use a parallel computer massively if you do leave one out, right? Again, if you have one sample, you always leave out 1 million data set, that would be a very long way. However, of course, it works, and just a small example why it works is basically the best explanation here. This is just, let's say, alluding to the n-fold and so on, but it's an interesting question how that works. So when you think about there's noise in the target function that we want to have, and there's a full data set, right, which would be this, right? And then we say now we want to have this validation I just explained to you, leave one out, right? And this means when we leave one out, in this little data set at least, for instance, it fundamentally changes the training, right? You see that. Basically, the algorithm will fit these 2 points, and we have a large, let's say, error here in the sense to this one point we didn't consider it because it's our test point, in a sense, or the validation point, to put it more accurately. Then I do the resampling, right? Now I basically put in this one, but leave this one out. And then I do the same again with this one. So this is this leave one out strategy with all the points in the data set. Admittedly, a very toy example here, just to get the message, what it means and why it works. And then basically you complete the average of all these errors. And once done this, you have modeled basically and can have a really estimate of saying in cross-validation this error is like that. And of course I pick the one that has a less error on this. So and this is let's say, very much possible in a systematic way. As you have seen, you go sample by sample. Still, we have always doing one sample is not really interesting. But that's how you can report. And an application example would be then this, right? We have done this just, and say, for instance, as you know here, that is a linear model, right? So we have seen a line here that the algorithm is doing, could be perceptron, and not caring in the moment exactly what it is. The important more thing is we leave always one out, estimate the errors, and think now about a decision. That's what validation is doing, deciding on a model. So we have to look at the error. That is an estimate of the out-of-sample error, because we talk about the validation set. And here's now a question of, for instance, H of the kind of hypothesis that we have in this particular sim is a linear model, or should we just rather use a constant? Right? And this is an interesting example where, for instance, you think about, okay, let's just use a constant, yeah? That's just no learning at all. That's a very simple example, again, to bring the message across. You can calculate the errors then on the validation set. You always leave one out, and you average again, and then you basically can see that the constant model is even better in this amount, right? Because the error, in the end, is smaller. It's an interesting aha effect. Which works particularly well on these 3 samples. Now in practice it would be probably not always the case. But just because you're measuring it, and now you have a decision support basically that you have in your hand with this validation set, right, that you have established. Now we come a little bit to the problem of saying this is computational very expensive, and I do now, have always leave one out, have lots of samples, 1 million times. Perhaps we do the same thing a bit more, let's say, deliberately, and say we do a 5-fold. So we always leave 5 out, train on the rest, and validate on 5. And the same I do again and again and again throughout the resampling strategy of always using the other samples. That was a question in the break. What do I do? And here and there, the data is just in this particular sample. If I would always pick the same, so to speak, then I would have lots more variance. I have much more problems of fitting the model in an accurate way. So this resampling strategy of doing it in this systematic way works very well, and of course in the terms of 5-fold compared to the leave 1 out, there's already huge gains in terms of less computational time needed, right? And this is by far the recommendation in practice. Use 5-fold cross-validation or 10-fold cross-validation, right? If you are, let's say, okay with some of the results, 10-fold cross-validation will do. If you want to be very accurate, go for 5-fold cross-validation. And this is an example where parallelization now will have lots of benefits, as we will see in one of the parts. Just a little bit explaining now, maybe visually, how that looks like on your training set, right? You have still the limited number of training samples, but you use leave 1 out, always 1, or you do the different k-folds. And of course you can steer k as you like. Here's an example of k equals 10-fold. So still you have all the training examples here in the pot being involved in all of that, but you pick always 1, and the others are involved in training, and repeat this just many times. And this is actually helping to get the bias very small in the data. It's still there. And if you here see basically just randomly resampling, right? Random splits in the data. For degree of polynomial, that is here shown on the x-axis. You see when we do that without some good strategy, just picking somewhere in the data set, we have lots of variance in the data of saying, wow, how is the error in the degree of polynomial 4? But we now have to pick and choose, and how we should choose from all those different lines. Should I use a polynomial to the degree of 8 or 6? There's lots of variance in the data, cannot be sure. The beauty then is, because of the kind of iterative approach in a systematic way, through this systematic resampling, where there are no random splits, right? We did it accurately, step by step with the folds. We can capture the variance and can do a very reliable estimate. Still using the training data that we had before. Not a new validation set, really the training data, because we basically have the bias in the data very limited. And this overall then has a better model selection process that you can do. And it's basically the key essence what you do now largely in practice. When you go outside in the field, chances are that you mostly use 10-fold cross-validation or 5-fold cross-validation. Right? And then it basically also enables early stopping. When you think about it, just another parameter of time t that you evaluate in a systematic way and think, okay, when I train 1 minute, 2 minutes, 3 minutes, 4 minutes, you can basically also do these studies to go to a good parameter of parameter point t inside the validation set, or using cross-validation to find the answer. Right, so in the, and then you pick basically the ones that, of course, in the validation set you do different studies, hence we will come to a part which we have here, a kind of more grid-like structure with all your parameters. You do your study, and in the validation then you will come to the one that had basically decided best to use this for model selection. Of course, think about it, should be done many, many times. That's why the expected value sits here. Otherwise, it will not work just by doing it once. But this is a part where the optimistic bias is very, very small, right? And this is a pitfall again when you use the training set also for basically the model selection. You will go to the bank and say, well, according to my training and testing, it will be 80% right. That is the optimistic bias. When they use it for real data, for unseen examples, it will exactly drop to 70, 60. Because you have done this mistake on putting this optimistic bias inside your model selection. And there is exactly now the point of cross-validation. If you use cross-validation, and then basically the bias is so small that this accuracy drop would be just minimal. So chances are that your customer will say still yes, okay, you reported 80, but we have just 78% or so. Right? And this is an interesting property really if you do it and see that in your real hands in the data. This is of course something what I would encourage you if you want to do it at home. Use that really once, do cross-validation, and don't be biased then because you will know the best parameters of Indian pines, also that we do now today together. But of course, try others out, and you will see that basically this is actually true. Right, so coming more to practice, libSVM has just this all implemented, and there's nothing very much more you have to add than just specifying -v and the number of folds in your SVM train. Everything else remains the same. You still want to have the right model parameters, right? You have C, you have G for perhaps the RBF kernel. Basically, you have your C part, all of this chosen. But now comes the point that we want to choose it, explicitly and search for the right model parameters, right? So what I will do now is something basically like a grid search and go through all of these parameters with cross-validation. And hence, here's the most computing site needed, right? All have to have an estimate of all of these parameter combinations, right? So it quickly grows in terms of complexity, and in order to report the best, one fellow of those will win that you have here in the grid, right? One of them will be a perfect combination of saying your RBF kernel gamma 1600 or 1000 or whatever will win. That will be the highest estimated accuracy out of sample. And this is what we will do now together. Perhaps before we dive into this, just a small video to conclude a little bit also on this kind of support vector machines, how they learn. It shows you a little bit, the idea. Again, I think it's clear with nowadays, these all are, very much not contributed to the support vector. You see the support vectors are mostly around here, basically this space. Every now and then they're very much high up, but this is of course something what we have thought of before. It is now going through different lines. It looks very similar like the perceptron learning algorithm, right? But you see, firstly, it's not so hectic with adding, subtracting vectors. It's always doing now this minimization that we talked about with this Lagrangian, with the optimization step, and coming to the minimization process iteratively over time. That's why when you have executed, for instance, in the libSVM, you sometimes saw iteration, right? It's an optimization step over time, minimizing your problem. Right, this is basically also, and it will converge then at some point in time of really then selecting those which are, having then basically the best margin possible. Okay, so let's do some practice together. Now we basically need the hands of everyone who is actually really actively on the machine. So we do teams, perhaps always 2 people together, roughly, of getting a parameter value. So your task is then just working on this parameter value, okay? So that we have a kind of group assignment here. So if here maybe the gentleman in front, if you're working on the cluster, then you basically have here, and you should really note that down now, right? You have 4 and 10. All others ignore 4 and 10. Right? That's your duty. And now the 2 gentlemen afterwards, you have 8 and 10. Then I proceed to the left. You 2, basically, you would have 8 and 10. 8 gamma C10. Then perhaps you can join as a team a little bit together, or you sure you can work on alone? you can decide now. Maybe do a team, right? I think you 3 in the second row, I will come to you in the front. You 3 doing 16-10. Okay, that's your duty. You in front, maybe also all 3 together, 32 and 10. right? And now think about, we're picking now a bit the space of the parameters. In a practice example, this would be much larger, right? You could start with 0.0 something cost, or 10,000, 100,000, so on. So usually there's some kind of rules of thumb again. You start 2 to the power of 2, 2 to the power of 3. These are kind of common values, or like the costs I have here. So I narrowed down this, and I have later on a slide showing you the whole grid search. But to have a kind of common task, it's important. So I continue on the other side. So when I take you, like, do you want to work together maybe on the left-hand side, right? Then we basically have you down for 104. Then we basically have you. You're happy to work alone, otherwise maybe go back one line. There's another lonely fellow working, maybe work together with him, if that's okay. You both have 8 and 100. So proceeding to the left, and please scream if I leave someone out. So the two gentlemen there, right, you have 116. And I put you all three together, if you don't mind. Basically, you have 32, 100. Okay? We will come, how you will submit, I will tell you, right? We will do it in front. But let's us just finish here that everybody has a chance of getting group assignment. So the gentleman and the lady on the back, right? You both are one team tackling 4 and 1,000. Then the 3 gentlemen in the row, right? You are head shaking, okay, you know what I mean? You're 8 and 1,000. Now proceeding to the right, there's a lonely gentleman without a laptop. You're not really computing right now, as I see, right? So you're moving over to the other team. Okay, very good. Then the 3 block in the back. Basically, you know what I mean, right? Okay, you have 16 and 1,000. And the remaining 2 in the back, you know, right? You have 1,032.
Are you working on Indian pines?
Yes, yeah.
And with validation?
Yeah, I will explain now, right? It was just a group setting. Let's see what we have to do now. Basically, you reuse your training script, but I recommend to do a copy. So basically, you should a little bit follow what I do, but use your parameters for what I'm doing, right? Is there anyone, by the way, that I forgot that has not an assignment? We are teams, so we have to work together. Good, excellent. Right, so what we have is basically our typical job script for training, and as we have seen, what we do in validation is a little bit similar. Oops, sorry. So we basically have a similar job script. Right, so let's copy that, perhaps name that differently, because we're now in a different process. So we don't train, we validate. Example. So that is the first step. Please make a copy of your training job script. That would be important. And name it differently. Like validate. Can also be model selection.
Somebody has questions, let us know.
Yeah, exactly. Just a simple copy in your home directory. Also make sure that you have already done the module swap cluster, right, aspect that we have now many times, that you're not stuck in an interactive session, because it will take a little bit longer now that some of these models run. So once we have done this, we have to do now, of course, a change, because we're validating. You have seen, we have to add here this interesting parameter file, right, which is here just adding, for instance, and that is what I recommend right now, not the 5, because it will probably take too long, but we were able to probably do a 10-fold cross-validation. And here's another one. Please do that on the Indian processed training. If you do it on the raw, it will also probably take too long for our execute. If you're at home, of course, please go ahead with the ROM, go with other data sets. Here, use please the Indian processed training set. It's a very small one, so that we actually can converge and have something from our Friday evening, and not sitting in front of the computer. Right, so all you add is nothing else than PSVM train minus V10. We keep of course, the different parameters here that we now have to tune. In my example here, you see I'm stuck in the old terms, according to whatever your assignment is, right? Which means here in this particular example, you have maybe 10, 100, or 1,000, depending on your group. So that's something to pick. Then we have the different types here, and this is of course also something we have to consider, because now we want to have the kernel parameter, and we said we stick to the kind of RBF kernel, which will require actually -g, right, if you remember, which is the other part. Right, so we need a -g for the kernel parameter of saying 4, 8, whatever your group assignment is. So once we have chosen that, we see -t0 and S type 0. We have to review our parameters again, because now we're switching to the radial basis function here, right? And we have already specified gamma, so what we need to do is -t2, right? This is a type of the libSVM for the radial basis function. We leave S as it is, so S0 is not a problem. And save. So what we did again, to summarize, we use the same job script we basically use for training. However, what we done, we added the folds here, telling PSVM train now actually it's cross-validation, it's not anymore training. The process in itself will remain the same, that's why it's the same executable. Right? Inherently it will do training on the validation set according to the folds. You know, train on 9, validate on the 10th. Do that 10 times with the different setups, randomly sampled, but in a systematic fashion, in the folds. These one basically are all inherent parameters, as we know from PSVM, you don't need to know. However, this is your group assignment, -c, depending on your group value. -g8, depending on your group value, right, that you get as a group assignment out of this matrix. Should be G4, G8, G16. -t2 means RBF kernel. And this basically are, again, inherently cache algorithm and so on. Use Indian process training. And if I'm not mistaken, you probably can also increase to 2 nodes. Can we afford 2 nodes for everyone?
We can try, sure. Some people will wait in the queue for a while, but maybe it's better to stick to 1 node. I mean,
okay, then we stick to 1 node. Everybody 1 node. It's also fair because we have a race for the grid search.
Sure.
Yeah, sure. Okay, so let's go, and we have a small data set. Remember, Indian processed training, right? So once again, before we start, everybody has his group assignment inside the script, yeah? If not, please raise your hand now. Okay, there's still a question? Yeah, if you have a question, please raise your hand now. Otherwise, we go ahead and submit the jobs. Okay, make sure you have module swap. Actually, I'm not sure myself, so I probably should do that myself as well. What?
You can check, yeah, if you run ML.
Ah, okay. Yeah, excellent, okay. Good. Then what we just have left is basically just QSub this validate example. Now the interesting surprise is for you, we use the same executable, but you will notice there will be no model coming out. Because we do an estimate of the out-of-sample performance, right? We don't create a model now. All what we do is do several times training, folding, average the error out, and we'll report an accuracy inside the training set that we misuse in a way for a validation process. But we misuse it in a very formalized way with cross-validation and thus keeping the bias small, and are still okay with it. Still having more samples to train, which means probably our model will be also much better trained. Right, so this will take some time, and if you have troubles, always raise your hand, even when I'm talking, because the others can help you. Right, in the back they will come to you and help you. I need to continue a little bit discussing now our parallelization benefits.
Just one question. Before we were executing with x equals flux.
Okay, there's reservation, of course. Yeah, I forgot that. Yes. That's right, that's right. Of course, I submitted without the reservation. You should submit with the reservation, right? I tend to always forget that because it's very rare that you have this reservation. It's just for tutorials. And I'm so much used in the practice that I rarely use that. But please go ahead and submit the job in the reservation. And how to do this?
Make sure your job starts. When your job finishes, you should have an answer, and we will fill out the theory code.
Yes, exactly. So I will talk now a little bit in the slides, and to encourage every one of you to be very active in the Friday afternoon, just once more, and then we're done. Right? Then we're done and can leave home, because then you really learned all the key essentials of machine learning. You did regularization, you did validation, we used training and testing, and we basically have now a very formalized way with this 6 lectures now to go to practice. Admittedly, here and there a little bit, let's say, the theory was a bit short, but still you're very much prepared for doing your first modeling in practice with real data sets. By really checking always regularization, validation, be prepared for overfitting, but you know all of this and this content of the lectures. Right, so the remaining time I would like to go a bit back now to the parallelization efforts. Why we do that as part of a computing center, right? We are here at the part of the parallel computing center. So you were wondering why we don't do this in the statistical faculty or in the math faculty. This is because we're most interested in the parallelization benefits. So where is now the key advantage of using parallelization for it? It reflects something what we said about C. And when you play around this, just as a hint for you, maybe in practice, they are differently implemented, the Cs. You will see when you go from one tool to another, that actually C sometimes is a bound and sometimes more a budget of errors, and you have to increase or increase and decrease it. It depends, for instance, some of my students use the R library, which is a little bit different here and there from the interpretation. So be careful when you take a new tool and just use the same parameter values for C. It could be that here and there this is a bit differently implemented. In the end, it's software, right? So what you use, SAS, MATLAB, R, or in this case, PSVM. So basically to determine the right C parameter, this is really something where HPC now helps. As you see, we have hell a lot of combinations. And this is just one parameter that we need, right? You don't know where to go. So as a single researcher, or engineer, you go through all of these and spend hell a lot of time of computing or finding out the estimate out of sample. So this is already a win. And when you think about what parallelization can do, this is the example that you just basically compute, where we break down the time for Indian pines, right? And there's a publication of us, which is admittedly already a little bit older. So with now our CPUs, in the last year, basically, or in the last 2 years, really, you get, of course, more speed up, better values, even than we got. So this is a little bit outdated. Still, you see a little bit the message when you have the unprocessed Indian pines. Basically, how much we can break that down, always to the different scenarios, which means one is really raw, which is the first scenario here. If you remember, when you look in the data set, you have an unprocessed one, the raw one, and then you have a pre-processed one, which is basically scenario 2. And what you see here is always what you can do in terms of different runtimes and breaking this down with parallel in terms of training and testing. Right, so when you use MATLAB here at one CPU, it's 15 minutes, roughly, to do the unprocessed training in one core. Now this is comparable to something what MATLAB times were, roughly. So when you go down and you add more cores in our PSVM, we came down to a minute, something below a minute, with 80 cores. So that is where you see it scales very wisely and nicely, but the problem is here we hit the I/O factor, so we cannot go mostly below that. Right? The I/O of reading in the data set and then also creating all the I/O output, that is something where we cannot really improve anymore, and that's why we stopped there. right? We could now go 100 cores. The Supercomputing Center has lots of cores to give. But here we see really an I/O kind of end to the problem. And then when we have the same here for, for testing, you see also it's 228 minutes, right? And this reflects again the 10% training set to the 90% testing set, right? This is a huge testing set now, and we will see that's why it's so much time needed to actually digest that, right? And also here with 228, so what you would have in MATLAB roughly, you basically use the parallel version of PSVM and go down again roughly to something like 4 minutes. And we also found that there we could have increased probably the course and get even a little bit more down there. As I talked to you earlier, basically the trouble here is only the I/O bottleneck at the end, and also we could have more cores here used because it's a kind of embarrassingly parallel problem in testing, right? You only test against the decision rule that is already there, one by one, sample by sample. So there's no optimization like here. However, the data set is much bigger, it needs much more time. Then the same actually here, so I will not really go into the details here. Here's a small bump which is related to the implementation. For a certain kind of part or sample, sometimes we have a not ideal data decomposition. As you can imagine, we go parallel, so we cut the data set internally, right, when doing this. And with this, we sometimes have a not perfect cut, and this explains this plateau actually in a sense of really not improving for a while. But then we go down to 30 seconds again, right, for training in the pre-process one. And this is again a time when you think about now, you have the MATLAB case here with kind of 3 minutes or 4 minutes roughly. Here with half a minute, it really gets to click and much more faster. And the most, of course, is then again when in the testing case, when you think now you go for testing, 50 minutes in MATLAB, something like that roughly, with one core, and then you can improve to almost a minute. So you don't have to move away, right? And say I come back in an hour, I just do it on my desktop, check shortly emails, and come back and have still my minute. So this is training and testing. What you now do is cross-validation. It's more computationally expensive because we train the model several times on the training parts of the folds, while the one fold is always taken away then for validation. So you do this multiple times, right? You basically, in a sense, do the speed up several times. If you do now cross-validation in MATLAB, it takes extremely long to find this, right? Especially if you think about, you're not a team like we here today. You are a single researcher, you have to do this all afterwards. You cannot give MATLAB all this grid at once, right? You have to do it once, twice, afterwards. And this is another parallelization strategy that should be now in your mind. So what we've done in all the lectures before, we always talked about we parallelizing this one cell. So this is something where parallel computing takes place in the sense of this diagram. One times training testing inside the cell. Right, but as we do this in parallel in one hand, we can also, in a parallel computing center like here in Ghent, we can submit all of them at once. That's what you just do, in a sense, right? All of the teams now at once are filling this grid. You don't anymore like in MATLAB R or so, you have to wait until your laptop is ready with this, then you go to the next, then you get to the next. So your speed up, again, over all of this parameter values is significant. And to give you some numbers, what it means for a daily researcher or engineer to work with this, I have here already a little bit the table prepared that we got. Basically, when you compare it a little bit with MATLAB times, right? And where you really see then, we have not only the inherent parallel benefit of using HPC, which means in each of the cores we are parallel with the modeling, we can also do the whole grid search at once. And that's what researchers do. They have a small script iterating over all the parameter values. And then on the other hand, also the other parameter values, it's called the grid search automated, and even their packages, like in scikit-learn, where this is already specifically supported, this kind of concept. So in a sense, you can say this all will be executed at once, all of these, let's say, different cells. Because this is all what you normally have to add up in time, right? Add up this, add up this. This is pre-processed data, serial, so MATLAB, right, versus here you basically have the scenario 2 in both cases, versus tenfold cross-validation in parallel. And here we have in MATLAB 15 minutes, and you do 1 minute in parallel. with 80 cores, I have to say here, I think. Right? And this is something where then, of course, importantly, we don't lose the accuracy. And here, just alluding to some of the other SVM techniques, right? What we didn't touch upon is exactly how the SVM is implemented. So there's another technique called cascade SVM, which more has a tree-like structure of creating SVMs, which is actually filtering over time basically lots of data out. You would have more like a tree structure instead of a big matrix that you fill. You do small SVMs everywhere in all of these kind of leaves if you want. You crunch the data in smaller parts, and then you add up basically them to the really final SVM you train on the survivors. That's called cascade approach. The trouble of cascade is you have not a complete global picture, which means here you create a SVM that has not the complete picture, and you pick here some of the support vectors or filter them out that could be relevant in the global picture. Hence, you drop in accuracy most of the time. However, this scales better in a sense than our PySVM, because we have still the metrics and go through all the samples and so forth. You have these different SVM approaches in practice as well. So if you go to an implementation, you will also see different ideas are implemented, and you could use them for different parts of the game. In other words, when you parallelize and you drop now significantly, like your MATLAB has 77% for the best parameter value that we don't know, right? We have to go through the grid search one by one by one by one, etc. We pick the best only at the end. This is here basically in MATLAB, and then we basically report those. And if this is now like 40%, we didn't gain anything, right? We have to keep the accuracy high in parallelization, and that's of course what the codes are doing. The same as DVScan that you had yesterday. Of course, now we're not cheating of making it simpler. In a way, this is a little bit cheating, admittedly, but this is another implementation, SVM Cascade. This, what you have here, is basically the same accuracy. In fact, you have, let's say, 0.2 more, which is not a big deal, but shows you they are completely different implementations. One is serial in MATLAB, the other one is parallel on an HPC machine. Now, when you think now what that means in terms of time gains, right? First, with our best parameter set, 14 minutes to 1 minute, you would say now, wow, that's not a really big deal, right? It's like 12 minutes, 13 minutes win. But think about it, this is the first and the best parameter set here that you don't know, right? When you now have a practical problem, you can now judge which of our groups now has the best result in terms of accuracy. And I'm waiting for your screaming very soon of telling me how much accuracy it is. But this is of course something to think about. You have to go through all of them, and then you quickly, in the MATLAB case, with 9 hours, basically the whole day, you do nothing else than grid search, one after another, one after another. While in the parallel computing case, you have just half an hour computing all the grid search, come back after a cup of coffee, chatting with friends, and everything is already there. And of course, in this levels, it gets significantly a whole working day to just half an hour. And this is, of course, an interesting aspect when you use parallel computing to that degree. And you can find more if you look now, of course, on the complete case, pre-processed and unprocessed. There are similar things like 3 days, right? Because the raw one will compute much more. As it is raw, we have a relatively low accuracy for the raw one. But still, it's like 3 days you use in MATLAB compared to just 2 hours with parallel computing. Right? So these are orders of magnitudes where now parallelization with HPC really helps scientific people or engineering people to create their modeling, which is not tedious anymore. You can do it very quickly. And this in a systematic fashion using cross-validation and so on. So all this runs actually, and when you look at home or so, these runs are also all uploaded in B2 Share. If you search a bit, there are very many of them because I tend to upload all the kind of things we're doing. You will see the job scripts, you will see the data, you will see basically the outcomes of all the times that we got here for all of the different runs, so that you can also maybe get inspired and compare if you want. Right. So, have you already some numbers maybe in terms of accuracy? Still computing? Okay. Right. Then let's hope that will converge soon. Let's cross fingers. right? But I have still a little bit of material, so it's not that I will fall out of slides, but of course it would be more interesting to discuss your accuracies, right? So, and you used Indian processed, right, for cross-validation and tenfold, right? So, okay, good. So, just like a little bit in practice, I would like to allude to some of the problems we have really in practice and why it's not so easy again. Now this data set you had here in the last couple of 3 days were really very well understood. They were prepared for this tutorial, right? In practice, that's not the case. But it is beneficial to work in this area of science or engineering and machine learning in general, because you basically see here situations like this. Now you would wonder why 10% might be interesting, right? In a sense, could be just a couple of percent now using cross-validation properly, and you maybe achieve this 10% already. It is often related to many money for companies, right? If you do some aspects like here in the example, it's very famous. Who knows the Netflix price challenge, right? From the media, it was happening a little bit more. Okay, no? Interesting. You participated even, right? Yeah, so it's like some of us here have some experience. That was basically an open challenge, and you see that very openly now in the internet. There are more and more of these challenges where they give the data out, a certain amount of data, a company. It's very valuable. Normally it's often closed data, as I said earlier. And they gave just a prize out of saying anyone who just have 10% improvement on the Netflix movie recommendation system gets $1 million. This is a real thing, right, I'm talking about. And there was a team basically using artificial neural networks and some smart ways before of massaging the system. And this is basically a prize winner that received that money just by having only, in a sense, 10% improvement. But for a company, you see, they are very much interested in that by just giving already 1 million out just for 10% improvement. So this is a message to you when you go to some company, chemical composition, whatever, engineering, materials, right? Whatever you do in the practice, in your jobs in the future, think about that a little bit in percentage could mean a lot, right? It might be, for instance, you can better use material, right? So you have not so much waste, basically. When you have good predictions in basically how your material is used, you can maybe save there some material. Only if you save for 5% can mean hell a lot to a factory, can mean lots of engineering savings, right? So this is one example. Really think about this kind of accuracy. 10% improvement could mean a lot to a company. Depends where you go, right? It doesn't sound much, but this is a good example why it is. Then another, let's say, field which is very much for you maybe perhaps is a job interesting in the future where more and more jobs are, predictive maintenance. Who has heard about predictive maintenance? Right? This is an extremely now hot topic where, if you're interested in the field, you get very good jobs using machine learning for estimating basically when certain parts of some engineering, could be anything, not only a wind wheel here, could be any kind of engineering device or kind of parts of the factory, whatever, could be actually getting, ready for maintenance. And this has something, we also say, yeah, well, I predict then that one part should be exchanged. It could be not an impact for a company. However, this is another good example why this is so interesting. So first of all, you have lots of data generated, so you can learn well from this machinery. Watnik-Scherboninki's inequality rings a bell. More n's, more samples, good win, we can have a chance to learn. So when we think now, wind wheels, okay, there's a part broken here or will broke. When I know that early, I can actually already, schedule a helicopter there. So I don't wait until the thing breaks, I exchange the part before this breaks. But when I do it when I realize it, when it just breaks this part and the wind wheel stops, it doesn't generate energy anymore. So all this time of waiting until the kind of the device or whatever is broken comes actually to this wind wheel is all dead. No energy is created by the wind wheel, which means very bad return of investment. Right? So what you want to do is predict this point before it's going to happen. And of course from previous data you have known already by these things you have here from the different kind of data coming out of these machineries today, and it's always constantly improving what you get out, you can have an estimate. And it's still often cheaper for the company to follow this estimate, basically, before you really let it basically running against a crash or a kind of a problem with the device, because then you can order the helicopter before the kind of device gets broken. So you kind of have a very short maintenance time, exchange the part, and the wind wheel can work again. Right? All of this can be scheduled before. You order the material, you order the team. In fact, what I forgot here to mention in this particular example from my colleague here, it is also a big issue to have certified teams for wind wheel repairs. Not every engineer can just do that. You have a very tough certification process actually to be one of those guys. So these guys are not only crazy because they tend to hang out of helicopters, they are also very valuable in terms of certification, get lots of training and certification procedures to repair that wind wheel. Hence, it's a very rare resource. And when this is now working on some other wind wheels and your wind wheel is broken, suddenly there is no expert that can repair. You have all the parts, you have the helicopter, but there is no expert to repair. So another time that went, and your wind wheel is not generating energy. Right? It's one example of predictive maintenance, which is extremely I think adding to insight because it looks so simple. You say just repairing a wind wheel, but you see the whole process of ordering material, getting the team on board, getting specialized teams, getting specialized helicopter for that. All of this process together, of course, means extremely an interesting, complex topic that you can actually predict. And with this prediction, you basically help of getting this as low cost as possible for the company. And this could mean a lot again to the company. Not only saying it's valid for wind wheels, right? It can be anything from kind of a device that can break in factories and so forth. Right, then a little bit, of course, as a scientist, I should close with some scientific data sets, right? Which we have lots of challenges with, and you are welcome to join us in the endeavor of science. I know from my experience in the class, of course, many of you will go to industry when they're finished. Think about a career in science. It's also very insightful and very much good positive things. Here and there the salary might not compete with industry, but you have lots of more travel, you see the world, you have international colleagues, you have the chance of being an international expert. So here's some of the fields where I just think we could not have more experts than we have right now. So I think the brain in particular, hence in Jülich there's this Jülich Human Brain Project, which is a European flagship project, bringing together all, let's say, players in neurosciences. This is a key field to study. It's hell a lot of data. We need many experts to look at this. And the key message is we have so many different injuries, we have MS, we have different diseases, unfortunately, that we still not really completely understand and can cure, right? So many of these things just scream for data scientists to be there. And the honest question is we don't have enough. You need a specific training, right? People that are interested to work in science. We just discussed it basically also the break here, that of course you need this valuable data sets. We had basically a key neuroscientist, a lady in our center called Katrin Amund. She gets the brains donated to work on for science. But it's not that Google brain gets like 20 brains a day. It's rather scientists get the brains. However, they need good PhD students, good scientists working on this on a daily basis to find more in a small step-by-step approach, some cures for diseases in the long term perhaps. It's not that everybody will end up with a Nobel Prize. You will basically contribute with your little Lego piece here and there with publication, here and there with approaches to the big picture, and then this could be very much rewarding out of my own experience as well. So now, of course, a little bit my own field where I'm mostly in, I think that's also a very nice field to study Earth science data sets. Not particularly remote sensing, I should say, rather Earth science. It's a very much interesting field. We have lots of measurements. Pangaea, as I told you before, this kind of data collection is around 80% to 90% underutilized. It's not used. People put in data, but we don't have the scientists to look at all of that. Right? There are lots of natural phenomena, like I said, for instance, the Koljefjord water mixing, these kind of things which then help to regenerate whole regions in Sweden. that actually have impact, right? This is a thing also what you should consider. They're just screaming as well. And the beauty in earth science data set is they're usually much more open than neuroscience data sets, right? That's why I particularly like this field. If you go to conferences like EGU in April in Vienna, or basically also the AGU just coming up in 2 weeks, the biggest conference is basically in earth science. You will see they have lots of data where we also have to find out very much if you want and have time, and so it's an interesting field to study as well. All right, so with this, basically we can come back to the exercises. Any news for the accuracy? Okay, some people say yes, okay. So I hear the first team. Please say first parameter and then your accuracy. Firstly, you?
So parameters is G is 8, C is 100.
100. G8, C 100. So we have G8 and 100 here.
And we both find 77.0302.
77.02. 03. Okay. Perfect. First team. Congratulations. Okay. Let's first parameter values, then please the accuracy.
C is 10.
C 10.
G is 8.
And G is 8.
Yeah. Accuracy is 74.
74. Okay.
5299.
5299.
Yeah.
So I keep it at this, as it is a little bit informal here on the board. Okay, so that tells us already a model selection, right? We probably rather want to have this instead of this. Still, you did very good work, right? Thank you very much, because everybody else had also done the work. Okay, there's the next one coming up.
C10
C10
and G4.
and G4 here, okay?
70.
What?
70.88.
70,
Yeah.
like this,
Yeah.
okay?
0.88.
0.88, okay. So we see probably around here is a hot area, right? We see here, okay, it seems to be already interesting area to be more in doing cross-validation runs around it, right? So let's see, is there another team? Okay?
C100, G16.
C100, G16. Wait a second, C100, G16, yeah.
76.4.
76.4. Okay, that indicates also a direction, right? So still we have this team having 77%, seem to be the best parameter set for model selection right now. Any other team? Yeah.
10, 16.
10, 16, okay. 10, 16.
76.069.
76.09. All right. In a way that was kind of expected, because we seem to move away when we are too, you know, now it's an interesting thing about cost, right? We seem to be allowing more cost. So basically we drop here in accuracy, even if it's just a bit small, but it's everywhere the case, right? When we seem to. We don't expect necessarily that perhaps here will be always a better thing. So we probably want to stop here in a practical situation, right? If you have now a big grid, this is important. Who else? Okay, yeah.
C10,
C10,
G32,
okay. C10, G32,
75.38.
75.38. Excellent, okay. Also kind of expected, perhaps, because we have this thing that here very high. It seems to be a very good parameter for C yet, but we don't know about the 1000 yet, right? So, next one.
We have G4 and C100, and then we have a score of 75.87%.
Sorry, G4 and 100?
G4 and 100 for C.
Okay. How much?
The score was 75.
75. Okay, very insightful. 75.87.
87.
Okay. So this tells us a lot already, right? So basically, this fellow has a very, very high chance here. No, but let's see what's coming up here, right? We're not done yet. So next teams.
G8.
G8.
C1000.
Okay, very interesting. So he was not waiting. It's like Lotteria.
Well, actually, I have first a question.
No.
There are two cross-validation accuracies. What's the first one and what's the second one? In the output, we have two cross-validation accuracies.
Okay, no.
One of them is 0.06%, and the other one is 75.79.
Yeah, that is what we want.
Yeah, and that's the one.
75 point?
79.
79. Okay. Well, a little bit now, you know, when you know as a scientist, you a little bit lay back now and say, okay, it seems like we found our fellow. But however, let's continue. And the others? Yeah, please.
C1000,
C1000
G32,
and G32.
73.91%.
73.9%.
91.
91. Okay, excellent. Thank you very much. We're missing still a few. 1004? Yeah.
76.
76.01. Excellent. We missed 1016. Yeah, the team with 1016 didn't came to a result, or okay, no result. Okay, what about the team with 132?
Not yet.
Not done yet. Okay, right. However, it's not so crucial because I think you agree with me. We could expect something, right? We can see now on the values that. If you think about that, this is a systematic process. It's not random lotteria, right? So we know what we're doing here. We know what our classifier is doing. So first of all, the C value, right? We change this on this direction, 76, 75, seem to be degrading. The more costs I put here, equally when I do less, it seems also degrading, right? So basically you would say the winner is this. Even if you have here the missing value in the moment, our really high expectation is not that this will be now significantly moving up, and in practice it never will be, right? Because we do it systematically, cross-validation, folds, we capture a lot of variance and all of that to have a really reliable estimate here. So, the same is actually true on the other side. When we think now, going to factor 1000 here, that here something bigger will come is not basically the case. Hence, the winner for your model selection process is C100 and gamma 8. Now, the interesting thing is, you're not done normally, right? We are done for today because we're nearly approaching the end of the tutorial. But now what you would do as a researcher is you pick this and train your model, right, on all the training data. And you can try that. If you train your model on these parameters, it will be less accuracy. This is really the best performance that you then get basically on your training set. Put all the samples in the pot now because you don't have to need this data validation set anymore. And there's a small bias inside, an optimistic bias as we discussed, by reusing that for cross-validation, but it's still okay. And you get a higher accuracy when you use this particular example. Now when you publish as a scientist and you just do training and tests in papers, for instance, mostly the reviewers, including me, when I review and other colleagues, we reject the paper. So my encouragement to you is when you work in this field, always do this grid search with model selection, because otherwise the reviewers will all reject basically your papers. Do that in advance to save you time, you know, of having a frustration by publishing just training and test. And the reason is because we want not to just review, to kind of reject the paper, we would know from experience it will be better accuracy if you do it. And you will find a better value in most of the cases, right? Right. Thank you very much for that. If you want, of course, you're invited to use a cluster more. My suggestion would be now training, for instance, on this set with 8 and 100 and see now the difference in accuracy, maybe when you compare to 10 and 32 or something. right? And this will be an interesting takeaway message for you in practice that cross-validation pays off searching the parameter. Now you could argue, and this is something we will see next week, when we have neural networks, we have a number of neurons, hidden layers, we have a multi-dimensional grid, so it's get quickly lots of parameter in practice. So there's things like particle swarm optimization methods where you just go along the best results. All things I cannot bring across today, but when you're in practice, of course, you don't necessarily have to have the static grid search, right? Good. I think we're done. Unless there's any burning question. Okay, there's a video that is summarizing all the stuff we just said today, basically about regularization, validation, data testing, validation. Because it's Friday afternoon, I think perhaps you can look it at home. The link is there, the YouTube video. And also, I'm not out of the world. If you have questions for this tutorial, I have an email address. Right, you can always send me an email. I try to be responsive. Of course, I cannot guarantee it on a daily basis. I'm a very busy man. But please feel free to contact me if you have an interesting project. We have already identified, I think, 2 or 3 that have an actual project where we can work together. That would be quite interesting. Otherwise, I see some of you next week, right, when we have the deep learning kind of tutorial. And for that, I would like to have Kenneth on the floor. And basically your colleagues, everyone from the Ghent Supercomputing Center, because I think it's also time to thank the gentleman that let you do all the practicals. You know, we're machine learners, we are knowing about HPC, but don't underestimate the work of installing the right software version of libsvm in a very, very nice, organized way, module load. You know, you don't have a kind of ambush there, don't be shy, come on, right? This takes hell a lot of time. The real versions on the real clusters that this all compiles. We just had, basically when we compile PSVM, the problem isn't one OpenMP library. Hence he is an expert, he switches just to another compiler. Right? Don't underestimate this work, right, of this development. So,
Thank you for coming.
yeah, welcome. Thank you very much. Thank you very much. See you next week with deep learning.